expressions in this paper. So I have a reason for this, it's squared. We would like to build up to a probability type distribution like the one that we averaged over here. To get there, we have to go through a few steps. The first is, I should say one more thing, or a little more, about our local unitaries, W and V. Since these are unitaries, we can decompose them. I'm going to call the eigenvalues of curly w little w sub L. Also, this is an operator that's pretty highly degenerate. Because remember, a toy model of it is just one qubit Pauli when there are n qubits. All those n qubits, on which there are a bunch of identities, make this very degenerate. So I'll call the degeneracy parameter alpha sub w sub L. Similarly, we can eigendecompose V. I will call the eigenvalues very creatively V sub L. I'll call the degeneracy parameters lambda sub V sub L. Now, at the risk of confusing you, I am going to pretend for the moment, well, for the rest of this talk, that these are actually non-degenerates. Just because I don't want to have to keep writing all those symbols, it would take a very long time. So don't worry about the degeneracies. I've been thinking about them, I thought about them, and I've been thinking about them with some collaborators. So everything works out when we put the degeneracy parameters back in. So when you see a ket that's just labeled by WL, think of this whole ket. You might worry, I'm going to be talking about measurements that an experimentalist should do. You might worry, since these are exponentially degenerate, that we have to perform a lot of measurements. We do have to perform a lot of measurements, but it isn't that bad. We can actually avoid the exponential degeneracy, but that's for another talk. Okay, so the first step toward our probability-like distribution is a complex probability amplitude. Well, let me say just a quantum probability amplitude. This is the first step on the path by which I'm going to build up our probability type distribution. I'm going to define this and then explain what it means. I'll call my amplitude A sub rho. And it depends on a number of eigenvalues of our local unitaries. Okay, what does this mean? Let's think about the following process. Suppose that we are experimenters in some lab, that experimental time runs in this direction. Remember, we are all-powerful experimenters. We can reverse time. What we're actually reversing is the parameter t, which is a little bit different from lab. initially, we prepare the state rho. Then we measure the eigenbasis of rho. Remember, the eigenbasis of rho is labeled by J. Suppose that the outcome is J. Then let's evolve our system in time under U. Then we measure curly W. Let's call the outcome W sub 1. Then we reverse time. Then we measure V. Let's call the outcome little v sub 1. Then we reverse time one more time with U. For a second time, we measure curly W. Let's call the outcome W2. That is one quantum process. Now, when we have a quantum process, we have a probability amplitude associated with that process. And if we take the square modulus of the amplitude, then we get a probability. Well, this is the probability amplitude, because we compared state rho, and we suppose that the outcome was J. That corresponds to a probability P and a probability amplitude P sub J. So the system is in state J. It evolves under U. We measure W, and the outcome is W1. Then we're in state 1, or in state W1, and so on and so forth, up until this final measurements yielding W2. So this is a complex quantum probability amplitude. Now, I said I don't look for any real experimenter to perform this process. How come? It wouldn't help us. We are going to need to calculate some combination of these. These are complex. If you just perform this process and gathered measurement statistics, you can infer the probability of that process. You could not infer the probability amplitude, which can carry a non-trivial phase. So this is just definitional. Okay, that was our first step. Let's combine these objects into a combined probability amplitude. So here I considered a particular trial of the process in which we got some particular outcomes from our measurements. Suppose that we run this process again and get some other outcomes. Suppose that when we perform this process for the second time, we again get outcome J here. But here we get an outcome that I'll call W3. And we reverse time. And after the V measurement, we get some outcome. I'll call it V2. And we reverse time. And this W measurement again yields W2. So we have these two different sets of possible measurement outcomes. These correspond to two different probability amplitudes. Let's put together the probability amplitudes. So my combined quantum amplitude I'm going to call A tilde. We construct it by taking the first amplitude that we discussed. Let's write it down here. So this is A sub rho, W2, V1, W1, J. I'm going to multiply it by basically the amplitude for that second process that I mentioned. So here the outcomes are W2 to W3, J. But actually, I want to take the complex conjugate of this. This looks a little funny, but I'll explain shortly why it makes sense. And taking the complex conjugate of a probability amplitude, remember, is sort of like reversing this process. Because if I take the complex conjugate of this, then I flip around the inner product, which corresponds to sort of the reverse process. So this complex conjugate is sort of in line with all the time reversals going on here. I'll do one more thing. I will sum over W1 It's just a bunch of inner products. The rho is here because we summed over J. That's the label for the eigenbasis of rho. This product of inner products, we can see, again, is very close to a probability. Suppose that W2 equals W3, or V1 equals V2. Then this actually reduces to a probability. It's very easy to see if rho is the maximally mixed state. Because suppose that W2 equals W3. Then this inner product is just the complex conjugate of that inner product. So this whole thing is a square modulus. That's a probability. And this too is a square modulus. It becomes a square modulus. That's a probability. And this 1 over d is a probability. So this really reduces to a probability in the simple case. And again, it differs a little from a probability because of the added time ordering. In fact, I should say, this thing is measurable, even though it's complex. So we can, in my paper, there are two schemes for measuring it. We can measure it with interference, and in the interference scheme, in no trial do we have to reverse time. In some platforms, reversing time is difficult. In some platforms, it's doable. So it's kind of nice when we have a scheme in which we can deal with the added time order correlator without having to reverse time. Also, we can measure this with weak measurements, using, say, cavity QED or superconducting qubits. I'm told that, especially with superconducting qubits, this is a near-term challenge. So it really offers hope for measuring the added time order correlator.
I mean, when you say measure, you measure A tilde directly, or you measure these separate things?
Yeah, the two different schemes involve two different types of measurements. In the interference measurement, we measure each of these. And for the weak measurement, we measure the whole thing. This is also like a probability because it turns out to be a quasi probability, or at least very closely related. I think, depending on your definition of quasi probability, we can call this a quasi probability. As I said, quasi probabilities turn up in quantum optics. Suppose that you have a quantum system and you say, doing quantum mechanics is great, but I really like dealing with classical phase space. That's the toolkit that I want to use. star V1 star. And I'll define big W prime as W3 V2. So you perform this trial, you get those outcomes. I say, please combine them in this way. For example, suppose that my curly W and my big V were Pauli operators. That simple example. Then, well, each Pauli operator has two eigenvalues, +1 and -1. So the possible values of W prime would be 1, 1, 1, -1, -1, 1, and -1, -1, because we're just multiplying together those plus and minus 1 eigenvalues in our example. Now that we've defined our random variables, we can define our distribution over them. By the way, I realized that I just erased Jarzynski's equality, which was down here. I meant to say it looks a little bit similar to this. That's one of the reasons why I say this is a Jarzynski-like equality. Here's something that we want to know, something we want to measure, and here's something that we can't measure. We're on to number 6. Again, since we're dealing with the out-of-time ordered correlator, we have to make things a little different so that that distribution is now going to be complex, not necessarily real. Or, yeah. I'll call it P of big W prime. I define it as follows. Let's fix some big W prime. For example, suppose that I choose big W prime equals 1, -1. Well, there are certain quadruples that satisfy that constraint. Each quadruple corresponds to one combined probability amplitude. So let me write out those combined probability amplitudes. Subject to my constraints. So this is, okay, I accidentally wrote this as a Dirac delta function. It's really a Kronecker delta function, so it should be a subscript. And I have another Kronecker delta function for big W prime. Then I just sum over all the quadruples, all the quadruples that satisfy these constraints. dispersal of information and the flow of time, it sort of makes sense that they should come together. Here's a way to put them together. It turns out to be useful because it provides fundamental insights into the added-time ordered correlator, a totally different sort of way of measuring the added-time ordered correlator. So this just goes to show that we put together quantum thermodynamic tools with high-energy theory and condensed matter physics, as is one of the goals of this iteration of the workshop. Some interesting physics can pop up. So we are, in a sense, standing on a bridge over the crowded Beijing streets, looking down at cars. If you see anything interesting, I would love to hear. Thanks.
I missed some point. Suppose you can measure this. It's a rho tilde. So why don't you just directly measure this OTOC? So you somehow you can measure this, but then you then introduce this P WW prime, and then take some do this derivative trick. So
you're right. So if you know A tilde, you can directly compute it.
why don't you just
Yeah, you just combine these in a particular way.
Right. So that's a way to show the result to I'm sorry, this is a nasty comment, but that's
It's a what?
this is a nasty comment. I'm sorry, but you don't have to do this. Have this Jarzynski-like flow. So if you can measure A tilde, then you're done.
Yeah, yeah. I agree. One reason why so there are two reasons why I cast this in this form. One is because the motivation was fluctuation relations,
Yeah,
and if not for that motivation, wouldn't have ever gotten there. Because I've talked to a lot of people, and they tend not to respond something like, oh, of course there's a quasi probability behind the added-time ordered correlator, possibly with one exception. It was more of, one of the responses I got was, how the expletive did you come up with this? And it was because I was interested in fluctuation relations. So that was the motivation that led to this sort of results and the next measurement, and so the measurement scheme and so on. So it's sort of suggestive, and also suggestive of how these ideas can be put together, or suggestive of how these two fields are very similar, and so they're worth exploring. The way that the Loeb-Schmidt echo and the added-time ordered correlator have similar flavors, so they're worth exploring together.
Yeah, well, in this case of Jarzynski, it's a miracle. So beta must be the inverse temperature. In your case, yeah, you said beta is not inverse temperatures. Yeah, in this case, it's just the parameters for generating functions.
Yeah.
So
Yeah, and I'm not saying that this is Jarzynski's equality. I'm just saying there are some ways in which it's similar. It's not exactly like it.
In Jarzynski's is very restricted. W must be energy difference. But in your case, it's more general.
Well, I
Rho
thought
can be anything.
I needed to define W and W prime in a particular way.
Yeah.
But
Yeah, I think I get it.
in analogy. Yeah, I'm definitely not saying this is precisely Jarzynski's equality. It's just similar in some useful. It's similar in some ways, and the comparison turns out to be useful in other ways. That's all.
Yeah, I think just amplifying that point and giving you a generalization. The observation of Kaplan and friends was mostly the fact that there's a way to rewrite Jarzynski relation in terms of a time-ordered correlator of a particular quantum operator, which is the energy difference between two different temporal positions for Hamilton. What you're saying is that if you want to measure an out-of-time-ordered correlator, there's a generating function, but that generating function has a structure that you just put forth here. And I agree with this, and it immediately suggests a generalization that you could sort of write down moments for higher OTOs by basically taking linear combinations with beta, beta prime, beta double prime, beta triple prime, etc.
Yeah, this is something that we talked about, and that's something that's going in the paper with Brian Swingle and Justin Dressel, that you can get out-of-time ordered correlators that have more time reversals if your quasi probability is longer, has more inner products in it.
fact that you sort of linearize the structure in the exponent where each W has just a V and W, a primordial V and W. Whereas an out-of-time ordered correlator is a much more an out-of-time ordered generating function is a much more complicated beast. As I was trying to tell you the other day, I can draw a picture.
Okay.
But so I think my first impression is that this captures a subset of out-of-time ordered correlators, not all possible out-of-time ordered correlators.
Yeah, this,
Yeah.
yes. Yeah, I have the one generalization to the longer quasi probabilities. I thought that was pretty general, but if I'm missing something, then I would be glad to hear.
Yeah, I just have to draw it for myself to see if I captured everything. But
So the question is that can this be generalized to imaginary time?
To what?
Imaginary time?
Imaginary time?
Yeah.
In what way?
Because on the right hand side looks like some kind of Boltzmann distribution kind of thing. And I mean, I do multi-color simulation, so I can easily get the correlators in imaginary time. So I wonder if there's some limit that we can compare this to the out-of-time correlators in the imaginary time and the real time. So I can get directly from the imaginary correlators to get some ideas about the real time.
Okay, maybe it would be worthwhile for us to discuss where precisely imaginary time comes in. In a lot of fluctuation relation papers, people say, well, this is a characteristic function if this beta is an imaginary time variable. And that's also in the Tucker-Lutz and Hungy paper. And just because I wanted to follow their proof and deform it as minimally as possible, I said the same thing. So initially I said, suppose that beta and beta prime are imaginary time variables. Then we can follow the same argument.
But maybe I can comment. The left-hand side is not an easy object to find in imaginary time.
Okay.
You see, it really requires a notion of time order,
Yeah.
which doesn't exist in imaginary time. What you can do is you can formally compute it in imaginary time in equilibrium,
And use this.
and then you have to do an analytic continuation. So the claim is that there exists an I epsilon prescription that gives you the top correlator if you do 4-point function in equilibrium.
Would you elaborate more about the experiment, especially in superquantum computing?
Yes. I'll try to give a very short synopsis because I can give a whole lecture on that. Let me say, I can draw a circuit such that we represent all of those n qubits. And so suppose that our qubits are going down like this, and up at the top is our curly W, and down at the bottom is our V. So we prepare our row, then we measure this quantity weekly. So this is similar to a projective measurement, but a projective measurement disturbs the system very strongly, so it can collapse our state onto an eigenstate of V. So we perform a measurement that only very weakly correlates our system with the ancilla, so we don't disturb the system very much. But we still get some information So that's a fairly well characterized process. But if you want later, we can discuss details more.
Could you tell me more about how is W and W prime, and I'm a little bit lost here. What's the relation between W and W prime to the W and the W operator there?
Yeah. So we said that we wanted to measure this A tilde rho in some actual experimental trials. When we perform a trial, we perform a bunch of measurements. The outcomes that we get are these. These are eigenvalues of the curly W and the big B. I said I wanted to define something analogous to thermodynamic work, which is a random variable defined as some combination of the outcomes of measurements in a trial. So I said, here are the outcomes in our trial. Let me combine them in these particular ways. Let me call these my random variables of interest that are, in some sense, analogous to thermodynamic work. So they're measurable random variables that you can extract from a trial.
Maybe it's stretching the analogy too far, but is there a notion of having a reverse trial and doing something Crookes-like? Or is this a meaningful expression in any way? Or
That's interesting. To me, time reversal comes in because we have U's and U daggers, and also because we have, okay, in particular we have this forward trajectory associated with A rho, and then this A star. The star means this is a reverse trajectory. So to me, that's where the really interesting time reversal comes in the A star. But I agree that that's an intriguing connection, and I don't know how to build an analogy with a detailed fluctuation relation like forces. But it is intriguing. And again, another reason why these two toolkits have the same flavor.
So this time is vector.